Okay, we're back. This is the 5 to 6 block on Think Tech Talks, here broadcasting from Pioneer Plaza on Ustream and Spreaker, and ultimately on YouTube and Olelo 54. And we have today a special guest, a visiting fireman, as it were, made available to us by Mike Markridge. And his name, sitting to my left, is Greg Wiegand. He's the senior engineer and chief technical officer of a mainland company called Microplanet. More than that, he is the inventor of the Microplanet voltage regulator, which we are going to find out a lot more about in a minute. I'm Jay Fidel. We're going to call this show Voltage Regulation and Tomorrow's Smart Grid, in keeping with our ongoing examination of energy in Hawaii and elsewhere. So, welcome to the show, Greg.
Thank you, Jay.
What are you doing here, anyway?
I'm here to talk to Hawaiian Electric and check on some of our regulators that we have in Hawaii, and just generally some business development with the solar industry here.
They need you.
Well, they're a little distressed at the moment.
Yes, we talked about that 1 hour ago in great detail. We called it the implosion of the solar PV industry. I don't know if you need to characterize it that way, but some people do. Well,
I can appreciate why some people would perceive it that way, yes.
So, I guess, you got some of these devices installed already here in Hawaii?
Yes, they're scattered around the islands, and we first came to Hawaii about 6 or 7 years ago, and we did a pilot demonstration for Hawaiian Electric, and it's kind of where it started in Hawaii.
So they liked it well enough to incorporate it in some installations?
Hawaiian Electric, no. It was originally part of their energy efficiency program, which then got spun off to
Hawaii Energy.
Hawaii Energy, which then took over by SAIC, so it kind of we kind of delayed pushing that program because we started to get a lot more traction in Australia.
Australia. We had somebody here from Tasmania just a week ago, and we were really surprised to find out how advanced they are in Tasmania.
Yeah, the whole Australian, that part of the world, actually is probably 3 or 4 years further down the road in terms of renewable energy than Hawaii, in my opinion.
No, I wouldn't disagree with that. It was clear. And the young man who was here was completely vital, may I say energetic.
Not like us, is that what you're saying?
It was a question of age, yes. Anyway, so first of all, before we get to the actual invention, which I am very, very curious about, what factors made you the inventor? You were in the right time, the right place, with the right training and the right, nurturing environment to become the inventor of this thing. Let's call it the Microplanet voltage regulator. What were those factors?
Well, as implausible as it may seem, actually, I worked in the motion picture industry, and
that makes sense.
There are issues there when you're recording sound, and you want to dim the lights. The normal way to regulate the voltage to the light, which makes it dimmer and brighter, creates noise in the lights, and when you have big lights, you have big noise. So I was kind of struggling with that problem one day, and the thought occurred to me that maybe there's a better way to do this, and I'm kind of a dropout physics major that got distracted by being a photographer and working in the motion picture business. I love it.
What a great career. You go where your heart takes you.
So, yeah, generally I think you'll find that disruptive technologies never originate in the industry that they disrupt.
Interesting point.
So I was perhaps naive enough to think that this technology could make a huge difference, and I still hold that position today, although it hasn't happened quite as fast as I had envisioned.
You mean a huge difference in the movie business?
No, I mean outside of the movie business.
Everywhere.
Yeah.
In the energy business.
In the energy business. So the company that we founded actually got started, which is Microplanet.
You were a founder of the company.
Yeah, I am one of the delusional founders of Microplanet, yes.
I like this company.
And
delusion is a good thing.
we got
I'd be bound by reality test.
Yeah, I mean, what's the fun in that? So we actually were basically got started by a grant from Bonneville Power Administration, and they wanted to study what they call distributed voltage regulation. So utilities for many, many years, so well over 30 years, have studied the effects of lowering the voltage by controlling their feeder line voltage. And you can save a significant amount of energy by doing that. But there's a limit to how much they can lower it because there's some uncontrollable variables from the distribution transformer to your building that they have no control over. So they said, hey, what if you could efficiently regulate the voltage right at the building? And that's where we came in.
So it's a transformer, isn't it?
Yeah, it's essentially, you can think of it as a variable transformer, and we can just tweak the voltage. And it has very low losses, so it's efficient to do that. There's a lot of ways to regulate voltage, but all the traditional ways either distort the voltage waveform and create other problems, or there's an efficiency issue. So, you know, if you're trying to save somewhere between 3 and 10% of the energy coming in, you don't want to waste 5% of it in the regulation stage.
Yeah, sure.
So our regulators, if they're sized properly, have an average about 0.7% loss.
Very efficient.
Very efficient. They're very fast. They react on a one-cycle basis. So
what do they react to?
Changes in the incoming voltage. And you can program the outgoing voltage very precisely. So
it's autonomous. You don't have to actually, send a message to it. It does it all by itself.
Does it all by itself. So essentially what utilities do is, because they have a very long feeder, they have a band of voltage that they deliver to your building, and it's plus or minus 5% of the nominal. So for a house, 120 volts is nominal. Most people have no idea what voltage is. They only know whether they have electricity or not. Well, when you flip your light switch on, the voltage to the light bulb goes from 0 to 120 volts. So that's the middle of the band, and it can be as high as 126 and as low as 114. And what we do is we practice what's called voltage optimization, and we hold the voltage right at the bottom level at 114.
That's what your device does.
And if the utility voltage drops below that, we can actually raise the voltage and keep it right there at 114.
I'm going to turn the voltage down on my phone here because I'm just kind of keeping in touch with your conversation.
So we started with a grant from Bonneville Power. We built regulators for what they call the Distribution Efficiency Initiative, which was a big 3-year study with 11 of their member utilities. And then we kind of branched out into more commercial ventures. And we came to Hawaii thinking, well, the cost of power is quite high here. This makes more sense.
How does a voltage regulator affect the cost of power?
When you reduce the average voltage that you get from the utility, the voltage from the utility bounces around all day long, and we just hold it steady right at the minimum. So however much that reduction is in real life represents a reduction in energy savings. And it's approximately, for every 1% you reduce the average voltage, you get approximately 0.7% energy savings and demand reduction.
So the so the utility is delivering this kind of jumping voltage within limits, and now your device is on the line. Your device delivers stable voltage at the nominal rate, whatever that is.
Yes.
And this somehow is more efficient, but this somehow saves energy. Where is the saving reflected?
It basically comes from reducing the losses in the electronic appliances and motors. So in other words, they give off less heat. And because all these devices are giving off less heat, you also have lower air conditioning load.
So you use less power. The guy inside who has the benefit of your device uses less power on his home appliances.
Yep.
Does that affect other things like amperage or wattage?
It does, but it's kind of maybe superfluous to the discussion, but different things react differently. But on the whole, it always saves energy, and we've done pilots in a number of commercial buildings and some residential. We did pilots for Actis at the Navy Housing and Forest City, and we've done everything from if people are familiar with efficiency standards, there's the LEED, silver, gold, and platinum, and we've done studies on LEED platinum facilities, which are supposedly absolutely state-of-the-art, and you still get 2.5–3.5% savings even then. So it's just the physics of it.
Yeah,
it's pretty universal.
But you're assuming in this discussion, are you not, that there is a jumping voltage at the point of entry? Suppose I give you a hypothetical. Suppose the voltage at the point of entry doesn't jump so much. Suppose it's straight, but it was 120 volts, whatever. I mean, perfect. Would that make your device unnecessary?
No, because you can split the conversation into two parts. So the really bouncy voltage is a power quality issue. And that's what they call a flicker. And if your lights are kind of flickering around,
it's the voltage.
It's the voltage changing rapidly, and we can fix that. But that's a different question than, what's the average voltage coming in. So if, for instance, the average voltage coming into this building was only 118, and you reduced it to 114, that's like a 3% reduction. 0.7% is 2.5%.
Easy to figure this out.
Probably wouldn't make economic sense just from that point of view. But if it was higher, what happens is the utility tends to run their feeder line as high as they can, so the guy at the very end still has enough voltage, because as you pull energy off the feeder line, the voltage drops.
It's a resistance on the line.
Yeah, it's line losses. So if you're close to the substation, you're going to have high voltage, like 122, 123, and then you can drop it, 8%.
Okay, so the idea is to take it when it's when it's too high, and to make it the right, and then you're saving energy at the end of it. You use less if you have the right level of voltage coming in. Yeah?
Correct.
Okay. I just wanted to get the basic parameters down. Now we're going to take a break. Having that under our belt, for digestive purposes, that's Greg Wiegand, Senior Engineer and Chief Technical Officer of MicroPlanet, an organization, a company that he founded, and or was one of the founders, I guess.
One of, yes.
And he is the inventor of the MicroPlanet voltage regulator, which we're studying today here on ThinkTech Talks. I'm Jay Fidel. We're broadcasting on Ustream, Spreaker, and ultimately on YouTube, and Olelo 54 from Pioneer Plaza. We'll be right back after this short break.
Aloha, I'm Nicole Horry for ThinkTech. For nearly half a century, the Hawaii Foreign Trade Zone No. 9 has brought the benefits of the Foreign Trade Zone program to Hawaii businesses and entrepreneurs. DBET, the Department of Business, Economic Development, and Tourism, operates Hawaii's Foreign Trade Zone program to encourage international business and economic development. The Foreign Trade Zone's mission is to increase the amount of international trading activity in Hawaii, thereby providing employment opportunities for the residents of our island state. For more information, see ftz9.org. I'm Nicole Horry. Mahalo.
We're back. We're live. I'm Jay Fidel on Think Tech Talks here on a Thursday in the 5 to 6 block from Pioneer Plaza with Greg Wiegand, Senior Engineer and CTO of Microplanet, talking about his invention, the Microplanet voltage regulator, and that's why he's here. We're talking about tomorrow's smart grid with Microplanet. So, to go to a question that you suggested in the break, namely, how does this affect solar? Solar is the word of the day. Everybody's frantic about solar on both sides of on all sides of solar. Everybody's frantic about solar. How does this affect, solar in the community, as it were?
Well, tomorrow I leave for Australia, and Australia is several years ahead of Hawaii in terms of implementation of solar. So Australia and Germany are quite a bit further ahead, and there's several ways to deal with the problem from a utility perspective. One of the main problems they have that affects people directly is that as I was explaining before the break, the utility tends to run the feeder line high at the beginning, so they have enough at the end because it tends to reduce as you take energy out of the feeder line. But that same reduction then inverts when you're running power back the other way. So instead of having a voltage loss,
like a net metering,
you have a voltage rise. And if you have enough PV on the system, they have a voltage rise. And their system for 100 years was based on the assumption that the voltage would only reduce. And now all of a sudden it flips.
Very interesting.
So it's really kind of turned them upside down because they set the whole system up so they start up here near the high limit and they design everything so by the time they get to the end it's not too low. So, to be fair to the utilities, this is a major blow. And
why?
Well, because for 100 years the assumption was voltage only goes down, not up.
So, but what's the negative about having it go back on, say, net metering and get higher as it goes back to the central place?
Well, the problem is it gets higher out here on the end. So if this is the maximum limit, 126 volts, and you take this curve down and you flip it up, it doesn't take very much energy before the voltage at the end of the feeder is now too high.
Too high.
Yeah.
Okay, so it would be higher than what the end, which is closer to the utilities generating equipment, to what the end would tolerate. What happens if the voltage that comes into that place is too high? What are the dangers?
Well, stuff will start failing prematurely because the losses are proportional to the square of the voltage. Sorry for the math, but stuff that's running starts getting hotter and hotter, and eventually it'll fail.
So it's heat. Voltage creates heat.
Yeah.
And if you're beyond the voltage the system is built to take, you're going to get heat the system is not ready to handle.
Yeah. So, PV inverters are supposed to shut off if the voltage gets that high, which doesn't make...
on the roof.
Yeah. I mean,
at the home.
At the home, the inverter, which takes the DC energy from the solar panel and converts it to AC and pushes it out to the utility, it is required to shut off if the utility voltage at the home is too high.
But?
Which doesn't help people that invested all that money in their solar panels. So
does it work?
Does it actually shut off? Mm-hmm. They do, yes. So,
okay, so let me give you an example. So if this is supposed to be at 110 volts, I don't know, what do you call it?
Nominal voltage.
not direct current, but alternating
current.
out of the inverter, say, and it goes too high because whatever happens on the panel or the inverter, then the inverter shuts off and there's nothing going back to the utility. Is that right?
Correct.
Okay.
That's correct.
And this is the way they all work?
Yes.
Sure.
It's the way they're required to work.
By the utility, because the utility doesn't want it too high.
Well, it's a safety consideration.
Okay,
yes.
fair enough.
It's a safety standard.
Okay, but doesn't that solve the problem you just described?
Well, it does, except unless you paid all that money for the PV system, and now
You're not getting,
You're not getting the benefit.
credits, on the net metering, okay.
So in Australia, one of the things they realized is that, for one, the government refused to let the utilities limit the penetration. So they were forced to deal with it, and so they formed a coalition and funded research on how to resolve this problem, and our technology bubbled to the surface. And so now in Australia, about 70–75% of the utilities are either using our technology or they're in serious trials to get the feel of it.
So using your technology means that there's a black box at the utility end of things, right, which regulates the voltage coming back from the homeowner on the return, on the net metering return.
Right.
That's going to hold the voltage low enough so it doesn't do any damage, doesn't get too high or do any heat damage to the utilities equipment there. Yeah.
Well, it's more a concern of that it's not too high at the customer.
At the customer's
connection.
Okay,
yeah.
so that's where you would put it.
So the utility.
Why don't you put it at the utility end? Isn't that easier?
We do, but the utility is required to keep the voltage within this delivery range. So we put in Australia, because they have a slightly different system, they follow the European system, where for one, it's 240 volts instead of 120, but they run what they call an LV feeder. So they take the medium voltage, they drop it down to 240, and then they'll run, 500–600 meters of wire, and they'll have 50 or 60 houses or small businesses on that.
Yeah.
So it's somewhat easier for them to use our regulators at their distribution transformer to regulate this whole group of people. And sometimes if there's a lot of PV on that feeder, that LV network, they'll put one in the middle of the feeder and one at the regulator. So
then you get double control on it.
Yeah, it basically takes, the regulator essentially trades voltage for current and vice versa.
Current means amperage?
Current means amperage, yes.
Okay.
So if the voltage is too high, we lower it, and we basically reduce the amount of amperage being consumed. If the voltage is too low, we take extra amperage and we convert it to voltage and make the voltage higher. So it basically exchanges one commodity for the other, so to speak.
But are you primarily concerned with the voltage returning to the utility or coming from the utility, or both?
Well, both. At night.
So it can work either way.
Yeah, at night, the energy is flowing from the utility, and everybody's cooking dinner, and there's no PV. And during the middle of the day, there's a lot of PV, so the energy may well be flowing back to the utility.
That's pretty crafty.
So it's a bidirectional regulation.
It's like a thermos. How does it, I always make the joke about the thermos. How does it know?
How does it know?
Anyway,
well, that's a whole nother show.
We're gonna
and I'll need charts and graphs for that. So.
Here we are with Greg Wiegand, Senior Engineer and Chief Technical Officer of Microplanet, inventor of the Microplanet voltage regulator, which is popular in Australia, and I'm very impressed. And we're on a Think Tech Talks emanating from Pioneer Plaza here. We're talking about voltage regulation in tomorrow's Smart Grid. We'll be right back after this break.
I'm Bill Spencer, President of the Hawaii Venture Capital Association. We do monthly luncheon programs with ThinkTech about things that matter to Hawaii entrepreneurs, investors, and business service providers. So join us on the fourth Thursday of every month at the Plaza Club. For information about upcoming events or to join our mailing list, visit hvca.org. See you there.
We're back. We're live. I'm Jay Fidel on ThinkTech from Pioneer Plaza. We have Greg Wiegand, Senior Engineer and CTO of Microplanet. Where's Microplanet's headquarters?
Seattle.
Seattle, where it should be, the land of technology. Inventor of the Microplanet voltage regulator, and he's here in Hawaii to talk about his voltage regulator and see if it can be adopted the way it has been adopted in Australia, where it has been adopted a lot. So we were talking about how it would work with photovoltaic, and I wonder. I mean, it sounds like this is an element of the smart grid. It is part of the smart grid. It's smart.
And I'm glad you use the word element because it's not the solution, but it's one of the tools that will eventually get people to where they're going. Now, the term smart grid means different things to everybody you talk to.
Some people, it's very amorphous, actually.
Yeah, I mean, to some people it's all about communication. To others, it's all about metering and, you know, knowing where your system is at and managing it. And to others, it's about, you know, automatic reconfiguration and self-healing. And they're all very lofty goals. And, you know, basically we're making it up as we go. So, you know, just to be clear, you know, there are a lot of moving pieces in this for the utility, and voltage regulation is just one of probably 3 or 4 major pieces they have to resolve. So,
what are the others? Just to put it in perspective.
Well, system protection, like basically they're circuit breakers. A utility has circuit breakers just like your house does. So if there's a fault or something shorts out, they can stop it.
Okay.
So system protection is a big deal. The other big problem is power quality and how steady the PV or the wind energy is, and that's really a problem for them because it frequently is up and down and all over the place.
So there are devices that you can put on the line to steady that power to smooth the curve?
Well, if you were to put our regulators right at your house, that would take care of that problem.
Suppose I put it on the other end of the windmill. I mean, on the windmill as the windmill is entering the grid.
That's usually medium voltage, and we can't handle that level of power. So the way a utility deals with that is essentially energy storage to buffer the variations, which is another emerging technology. And
storage or buffer, I mean, is it the same thing?
Yeah. So they store energy,
yeah.
And when the cloud comes over the PV, yeah, suddenly they need more energy, so they push energy onto the system.
What is the state of the art on that? Because, I mean, you keep hearing that there really is no efficient way to do that. We don't have that here. We have some very limited installations. Extreme is the manufacturer, but we don't have enough of it to make a difference.
That's not my area of expertise, but I know that there are a lot of different ways of redux flow batteries and, you know, lithium-based systems, and, you know, it's
batteries.
Typically, it's batteries, whether there's chemical storage or traditionally. So it's really not my area of expertise, but it is one of the unsolved problems in the smart grid.
Do you agree with me? I've had this recurrent dream of a capacitor about that big, okay, which would hold a charge until you wanted it. And if you put a lot of these things together, it acts as a battery, and it's cool, and it doesn't burn, and it can make you richer than Bill Gates ever imagined.
There are what are called supercapacitors that are vying for that market, and again, it's not my area of expertise. I know EPRI, which is the Electric Power Research Institute, has been testing some of that stuff, and nobody's got the golden bullet. But here's an interesting tie-in. So protection, energy storage, which buffers the volatile nature of renewable energy. So as we discussed earlier, when you reduce the voltage, you reduce the amount of energy. So my proposal is, if the utility wants to install this, they should set the regulator right in the middle, and if they need more energy, they can reduce the set point by, if you connect it to a communication network, you can talk to all these things, and you can reduce the set point, and you're going to reduce the amount of energy required.
That's the current again, the amperage.
Yeah.
So I can reduce my voltage, and in the process I can expand the amount of energy that's actually flowing through the line.
Well, if you reduce the voltage, you actually reduce the amount of energy required
To do the same job.
to do the same job, essentially.
Yeah.
And if suddenly the wind picks up and you've got too much energy, you can actually raise the voltage. And the load that's being regulated will consume more energy. So the physics of this is exactly the same as storing energy. And if your voltage drops, you pump energy in because you need more energy. Well, you just invert the logic and you go, well, if you need more energy, drop the voltage and you consume less. If you have too much energy, raise it and you consume more, which balances the system out. Because the problem for the utility is, if they have too much power and the load is small, then the frequency starts to rise, and that's very upsetting to things.
So you reduce the voltage, you get more energy, like at night.
You get more usable
Where there's not
energy.
so much solar, and you want
Yeah.
more energy to come back into those houses. This will give you more energy out of the same amount that's entering the line. Am I right?
Well, sort of. Let's just say they have a 5 megawatt generator, and their load is 4.9 megawatts, the total load. In theory, if you had regulators on a significant percentage of the load, which I admit is a lofty goal, and you lowered the voltage, it would go from 4.9 megawatts to, whatever 4% reduction of that number is. I don't know, 4.5 megawatts.
Okay.
If you raise the voltage, you would have more load than you have generation, and the generator frequency would start dropping, and that would be a problem.
Mm.
So the utilities challenge, and it's a significant challenge, is they have to balance the load with the generation. And to add PV and wind just really complicates it for them, because suddenly generation is doing this when, for the last 100 years, it's been very flat and very controllable. And, they know statistically how much load they're going to have in the peak of the day, so they turn more generators on, and then they turn them off later in the evening. And, they had all that stuff worked out, and now the apple cart's tipped over and they're underneath the apple cart.
So this helps them. It's not a battery like a battery would be a battery, but it can make more or less out of the same, and as a result, it's kind of a mini battery.
It can help them. It's a potential method to help buffer help balance the amount of available energy to the load.
Battery without a battery.
Yeah, and I mean, one of the potential value of this is that it doesn't require a battery, and the battery is never going to run dry. So you can use this any time of day for as long as you need it, and you know, the statutory requirements of the utility actually allow them in emergencies to go below or above this for a short period of time if they need to stabilize the system. So grid stability is a major issue for them.
And this can help them achieve that.
And it can be one tool that could help do that.
Yeah. So
Yeah.
you get a cert, but you wouldn't rely on this alone. Is that what
No,
you're saying?
no. This is one piece of a much bigger
Engineering question.
engineering question. And, you know, countries like Germany and Australia are dealing with the same issues, and they've, you know, Germany has tried some different solutions, and they've kind of realized, okay, that gets us a little further down the road, but maybe not far enough. And Australia kind of came along later and looked at what Germany was doing and said, all right, well, this has limitations, so let's kind of leapfrog.
That's the way it
Yeah.
works, right?
That's the way it works.
The power of innovation.
And, you know, they take a little more risk, and okay, if it works out for them, great.
So you learn.
More people will adopt it, and if it doesn't
So,
work out,
We're not adopting this in any great numbers here.
not yet, but, you know, I'm pretty persistent, so.
Okay. Are you the only one in the field? Is somebody else doing this?
No, not exactly what we're doing.
Really? And so you have a patent on it, of course, or multiple patents.
Yeah, we have multiple patents, and
Well, that's pretty interesting. Is anybody, you know, behind you looking over your shoulder
yeah,
trying to do the same thing?
you know, that's kind of a business question, and typically what happens is the big players watch
Sure, they should.
these little
The American
experiments,
way.
and then you know, if we succeed and we start taking off, they'll probably just buy us.
Of course. I didn't think of that. Of
You
course.
know, it's the cheapest way for them.
Yeah,
That's
yeah.
traditionally the way it's done.
Yeah. Well, I mean, this sounds pretty promising. But what, you know, for a utility, say Oahu, okay, because we don't have a statewide grid. What would it cost to incorporate this kind of technology?
Well, those are good questions, and of course, it wouldn't happen overnight. It probably wouldn't even happen in 10
you
years.
roll it out in increments.
But you know, you pick the worst feeder you can find, and you start there, and you put it in, and you use it, and you test it, and you measure it, and then you go, okay, let's take the second worst feeder, and then the third worst, and you know, then you incorporate the regulator into the transformer, which they're beginning to do in Australia, and so it progresses in that slowly, surely kind of fashion.
Well, what about the, you mentioned that it was autonomous, but also you could send messages to it. So I guess it's built for both of those
You
possibilities.
can do either, yes.
Yeah, so what about the notion of that? I mean, should we do that here? Should we install it with both possibilities and also message it?
Basically, it's the same unit, so
It's the same, you know, okay, no change.
yeah.
And would you put it on both ends in order to get to this testing phase, or would you just put it at the utility end of the line?
Well, that points out a fundamental difference between the European system they use in Australia and the U.S. system. So in the U.S., typically they'll have a distribution transformer, and they may have, speaking in residential terms, they may have 6 houses on one transformer. So the best implementation would be to put the regulator up by the transformer and feed all 6 houses.
Yeah, it's just a matter of efficiency.
So-
How big is this device?
Well, they're basically in proportion to power. So the smallest ones, which would power like a house, an American house, is, you know, like this, about that deep and like this.
Well, I could go and buy it. Right now, I could go and buy one from you and put it on my house, on my solar PV house, right?
No, actually, we don't make the residential model anymore. We may reintroduce it. That's part of what this trip is exploring. At the moment, we make 3-phase regulators for like convenience stores and small grocery stores and stuff of that nature. You know, it's a long way from, for instance, this building that you're in. You know, you couldn't just slap a regulator on this whole building at this stage.
Could you build one that would be big enough to do that?
Well, ultimately, maybe, but
It's not available right now.
No.
Okay.
And just because of the physics of it, you would probably approach big buildings by putting a regulator on each floor, because typically they run the power up from the basement up to the top. So it's the same physics we talked about earlier, that the more energy you take off of that circuit, the more the voltage drops. So the voltage in the basement here is going to be higher than the voltage on the top floor.
So why did you get out of making the small ones for the single house, and why then now would you go back into that? I mean, is it a market question?
I think the solar issues probably are swinging it more in a, you know, it all boils down to profit. So for us, it was more profitable to go into like convenience stores where they're open 24 hours a day and they use a lot more power.
Yeah, and you can show them better numbers on efficiency that way.
Yeah, and houses really are somewhat problematic for reasons of standard issues, but houses typically don't use that much electricity. So to sell it to
Why not
you,
make that much difference?
yeah, to sell it to you as a homeowner doesn't make all that much sense if you're only looking at energy savings. But when you factor all the solar issues and power quality issues in, you know, maybe the numbers make sense. That's part of what I'm exploring here on this trip.
Wind is not part of this exploration.
Well, wind is just another distributed energy resource like solar.
So it could equally be of equal interest
Yeah.
to a wind developer.
Yeah.
Well, I get the feeling, correct me, but that we are, when we talk to you, we are entering the world of the smart grid. And it's a difficult world to get your hands around because there are definitional questions about what it is. But we take a little piece from there, we'll take a little piece from there. One technology may not be the answer. In fact, your technology may not be essential in the smart grid.
It may not.
And some other technology or a combination of technology. So it sounds to me like we're pretty early in the game on smart grid. We don't really have it worked out yet as to what you need to make the grid smart as people expect it should be.
Yeah, I mean, it's truly a conceptual, it's a pie in the sky concept and pretty lofty one. And, you know, to really bring it to fruition is probably take 10 or 20 or 30 separate technologies. Communication, you know, metering. In America, what smart grid basically means is let's put meters in and at least find out what the voltage is.
But that's only a part of it.
But
and I think people who believe that that's the full extent of a smart grid are not informed. It's much more than that.
Yeah, and then when you have that information from quote-unquote smart meters, then you get into real-time pricing, which is all about the utility trying to not have to provide as much power at the peak, because that costs them a lot of money, and anything they can do to reduce that peak is very valuable. So that's where you get the conversations about peak time pricing. And you know, there's a lot of work being done on appliances that communicate with the utility and say, well, we're in a peak situation, so I'm not going to turn on right now. I'm going to wait for half an hour.
What about the peak time pricing? Is that your next invention? Are you working on that now?
That's not anything I really deal with other than what we talked about earlier, that you could actually affect the peak by reducing the voltage if you start in the middle.
Okay, let me reframe the question, Greg. What is your next invention?
Who knows? I'm hoping to retire. My next invention will be small, like this.
Okay, there you go.
Something that I don't need a truck to move around.
That's Greg Wiegand, Senior Engineer and Chief Technical Officer of Microplanet. He's the inventor of the Microplanet voltage regulator, which is a very interesting device, and we know more about it, although I wish I was an engineer to fully understand. And we talked tonight about the voltage regulator and tomorrow's smart grid in Hawaii. And this is the kind of discussion we have to have. We have to understand what you're doing, what your competitors are doing, and how all these elements are feeding into a better grid for us. This is Think Tech Talks, emanating from Pioneer Plaza. I'm Jay Fidel. Thank you very much for watching, and thank you, Greg, for coming on the show.
Thank you, Jay. It's a pleasure.
Aloha.